I'm Brian Prier, tutoring high school physics. Today's topic, electricity in a magnetic field. If you have a charged particle moving in a magnetic field, it is going to feel some force. We can describe that force using the following equation. Force is equivalent to the absolute value of Q, the charge, times the velocity of the charge, times the strength of the magnetic field, times sine of theta, where theta is the angle that the charge is moving with respect to the magnetic field. Note that if the charge is not moving, i.e. the velocity is zero, then it will feel no force. Furthermore, if the charge is moving either for or with the magnetic field, in other words, if it's moving 180 degrees or 0 degrees with respect to the field, then sine of theta becomes 0 and it also experiences no force. But typically you won't have to calculate problems like that because they're just so easy. Instead we'll have problems like this, where we do have a charge moving and these arrows represent the magnetic field. The charge has moving at an angle of 45 degrees to the field with a velocity of 5 meters per second and a charge of 2 coulombs. Now this is positive 2 coulombs. You could have negative 2 coulombs, but those won't matter in this particular equation because we're taking the absolute value. And the magnetic field has a strength of square root of 2 teslas. Now a tesla is a Newton per ampere times meter. Just keep that in mind. Okay, so using this we can start trying to calculate the force that this particle is going to experience. So Fm equals the charge on our particle is 2 coulombs times its velocity 5 meters per second times square root of 2 teslas times its angle sine of 45 degrees. Okay, so let's start going. 2 coulombs times 5 meters per second gives us 10 coulomb meters per second times square root of 2 teslas times sine of 45 is square root of 2 over 2. Well, that's useful. So then the square root of 2 teslas will be multiplied here, and we'll simply get, let's see, 10 coulomb meters per second times 1 Tesla. And so that leaves us with 10 newtons. Question though, in which direction is the force going to face? Well, we're going to be using something known as the right-hand rule. So if you take your right hand and extend it like this, so that you're forming gun with these two fingers, and then you have your third finger extending perpendicularly, well, we have something we can use. The thumb represents the direction of the velocity. This represents the direction of the magnetic field, and finally this middle finger represents the direction of the force. So you'll note, of course, that the thumb and forefinger are perpendicular to each other on the hand, so the velocity and the magnetic field should be perpendicular to each other. Well, that's not always the case. So if it's not the case, simply point the thumb in the direction of the component of velocity that is perpendicular to the magnetic field. So in this case, forefinger with the magnetic field, thumb points upwards because that's the component, and finally we have our middle finger pointing into the page. That means we are having a force of 10 newtons into the page. Okay. So what if you have a wire in a magnetic field? Well, if this wire is carrying a current, then the wire itself will experience a force because it's got a bunch of charged particles moving within a magnetic field. The formula to describe that is force equals the strength of the magnetic field times the current in the wire times its length times the sine of theta, where theta, of course, is the angle of the wire with respect to the magnetic field. Okay, so here's our diagram, and you notice I've drawn all these x's. That simply means the magnetic field is being pushed into the page. Alternatively, you would draw circles with dots in them, which means out of the page. But this one's going into the page. Okay, so let's try and work out the force. Force equals the strength of the magnetic field is 5 teslas here, times the current in the wire is 2 amperes, times the length of 5 meters. Now, the sine of theta, in this case, we notice that the wire is perpendicular to the magnetic field. So the sine of theta is sine of 90 degrees, which is just 1. So we can omit that from the equation. And instead just run through. When we get 2 times 5 is 10 Tesla amperes. I'm cheating a bit and not simplifying the units, because that would simply be newtons per meter. And so we finally have 5 times 10 gives us 50 newtons. So the force felt by this wire is 50 newtons, but again, in what direction? Right-hand rule. This time V is going to be pointing in the direction of the current. And so here we have the current pointing this way, the magnetic field pointing this way, and so we have our middle finger pointing up, so the force felt by the wire is going to be 50 newtons upwards. Alright, to recap. If you have a charged particle moving in a magnetic field, it will experience some force as long as it is moving and is not moving either with or against the magnetic field. The formula for this is the force is equivalent to the absolute value of the charge on the particle times its velocity times the strength of the magnetic field times sine of theta, where theta is the angle of the charged particle's path with respect to the magnetic field. The strength of the magnetic field is measured in teslas, which are equivalent to newtons per ampere times meter. And so using that formula, you can just calculate that force. However, if you have a charged wire in a magnetic field and it's experiencing a current, then it will also experience a force because it's simply a whole load of charged particles moving in a magnetic field. We can calculate this by the equation force is equivalent to the strength of the magnetic field times the current in the wire times its length times the sine of theta, where theta is the angle of the wire with respect to the magnetic field. Whenever you're trying to find the direction of the force, use the right hand rule. Simply point your forefinger and thumb so that they're perpendicular to each other, and then finally bring out the middle finger so it is perpendicular to both of those. The thumb represents the direction that the charge is moving. In the case of the wire, it will also be the direction of the current. Your forefinger represents the direction in which the magnetic field is pointing, and finally your middle finger represents the direction of the force. Alright, that's all for now. Again, I'm Bryant Prier. See you next time.